All right, now we're going to recap kind of our overview of epoxide opening under different conditions, and we're going to do some predict the product. So what did we see with the last video about opening epoxides? Well, if we had a neutral epoxide and a neutral epoxide needed a strong nucleophile to open up. And that process was driven by sterics. So if we had a strong nucleophile and an epoxide that was neutral, that nucleophile was going to add to the more sterically accessible position. So if we have a primary side and a secondary side, the strong nucleophile would add to that primary side. So driven by sterics. If we have a cationic epoxide, the addition was driven by, the cationic epoxide. How would we get that? We would react the epoxide with acid that would protonate the epoxide, and remember that asymmetrically weakened the bonds of the epoxide, and then the nucleophile added to the weaker bond. And that was really driven by electronics. What do I mean by electronics? What I mean is which side of that epoxide, which carbon of that epoxide was more capable of being stable with a partial positive charge. And the more substituted side was better at holding the positive charge. So that's what we mean by electronics. It was governed by electronics. That's what we saw. So what's going to happen here? This is time for you to pause the video and predict this product. All right, great, you did that. So sodium methoxide and a strong and a polar aprotic solvent, strong nucleophile polar aprotic. This is going to be the neutral situation, right? We don't have an acid. We don't have anything that would allow this oxygen to pick up a proton. We just have a strong nucleophile, OCH3 minus. That strong nucleophile could add to either partial positive side, the negative flows to the positive, but it's not going to add to the side that's harder to get to. It's going to go to the side that's easier to get to. This side is kind of a tertiary position. This is a secondary position. So this methoxide is going to add to that secondary position, opening up this epoxide ring, which generates this intermediate. I'm just putting a line to the methyl instead of writing OCH3. An important point here is that OCH3 added to this carbon, to the antibonding orbital on the back side. That's why we have this now as a dash instead of a wedge. We have this basic O minus. We then are going to add the second reagent, which is weak acid, and that's just going to promote that acid-base transfer to make the alcohol product. So that's going to be the product under these strong nucleophile conditions. What about the next predicted product? All right, so saw what happened with the first one. What's going to happen here? All right, so you've paused the video, you've taken the time to predict the product, and now we're going to get started on working it out here. So what are these reagents? Well, we have a strong acid, H2SO4, so this is our acid. And then what do we have down here? This is our solvent, and we've also seen it act as a weak nucleophile in lots of reactions. So this is our nucleophile. And again, it's a weak nucleophile. It's not going to be strong enough to open that epoxide by itself. So what's going to happen in this reaction? Well, I'm just going to represent this whole H2SO4 by just H plus here. And what happens when we have H plus and neutral oxygen? We're going to protonate. So sure, that oxygen's going to protonate, that oxygen's going to protonate, but the take-home message is that this epoxide has to protonate to react. So that's kind of the first thing that's going to happen. So that would generate this protonated epoxide. And again, which of these bonds is going to be weaker at this point? The weaker bond is going to be to the more substituted position because that position is better at stabilizing that partial positive charge. So again, I'm going to redraw this intermediate like this, where we're accentuating that this is a long bond on this side, and this is a little bit of a shorter bond on this side, because there's a pretty large partial positive there and a much smaller partial positive on that side. We're weakening the bond that allows for that partial positive to have more stabilization. So at this point, we have a weak nucleophile around. It's going to break the weakest bond, and that bond is that position right there. So it's going to add there. That's going to open that up. That would provide the structure here. And then just like in all of those SN1 reactions that we've talked about before, we're in an excess of this CH3OH. We have a protonated nucleophile here. And again, there's a lot more of the solvent molecules around than there are of any of these individual molecules. So this equilibrium doesn't really lie on one side or the other. It's about 50-50. But if there are way more of these molecules around, it is going to push the equilibrium to this side, where we will have full formation of that product. And again, let's point out that when the nucleophile added to that carbon, the stereocenter inverted. That CH3 was a dash, and in the product, that CH3 is a wedge. And if we did R and S for this one, it would be the opposite of that one. So that is the gist of those predict the products. So yeah, you're looking good. All right.